So, welcome to the episode 16 of Probability and Statistics for Engineers, and I am Mohammad Momenzadeh, the presenter of this lecture. Today we will discuss about some topics about the discrete distributions, and we will discuss about the multinomial probability distribution and hypergeometric probability distribution, and if we find the time we will discuss about the remaining parts as well. But at the beginning of this lecture we will start our discussion by one example and a quick review about the binomial distribution for a discrete random variables, and after that one we will go forward and talk about the remaining part of the distributions. I want to mention about these things that at the end of the day, when we discuss about all discrete distribution, we recap all of them and put them in one slide, and you will see that how it can be worked for different type of the distribution. So don't worry if you cannot catch all of them in one at once, and you may have some problem by mixing this information together. So let us take a look at that example and see that how can we have a quick review about the binomial distribution. So I describe the question by the word instead of writing the question completely over here. So we have 8 for multiple choice question over here. So you may see that type of the answer sheets in your life for sure, that you should answer the question by filling the blank places over there. For example, this is the choice A, B, C or D on your answer sheets, and over here when you want to answer the question you should fill one of that actually blank places over there. So we have some assumption over here. Assume that one student who attend the exam wants to answer to 8 questions like this, and assume that this student answered the question only by filling one of them. For instance, he answered the question 1 by C, the question 2 by B, D, A, and B again, C and B, for instance. So this is one type of answering of the questions, and assume that the student only fill one circle or one choice out of 4 choices for each question, and he answered the question by random. Means that he just like things that we did it over here, he did the same thing at the exam. I want to see that what is the probability that the student answer exactly 3 questions correctly. So of course there is the another assumption that one choice is a correct answer for that question and 3 of them are wrong, are not correct. So over here, first of all, it's important to understand the concept to answer to that question. If X denotes the number of the correct answer, so we have one random variable that we use it to determine the question. So X denotes the number of correct answers. So this is the X, and I want to know what is the probability of answering exactly 3 questions correctly. So at this type of the statistical experiment, first of all you should think about the characters of this question. I mean, we just answer that a student indeed answers to 8 questions, so it means that some statistical experiment repeated 8 times. So the n, or the number of the statistical experiment that is repeated over here, is 8. The another thing is about each of these question. For each of these question we have 2 possible outcomes. One is answering the question correctly, the another one is answering the question wrong. So the probability of answering the question correctly is 1/4 because one of the answers are correct. and the probability of answering the question wrong, or the Q, is equal to 3 over 4, and this number holds true for all cases over there. Means that for the question 1 this probability is 1 over 4, for question 2 is 1 over 4, and so on. I mean, it's not changed, it's invariant. In all of this experiment, the probability of success or answering the question correctly is 1 over 4. The probability of failure or answering the question wrong is 3 over 4, and it's constant, is invariant for all of these cases from 1 up to 8. And the most important thing is about the random variable as well. Random variable denotes the number of correct answer or denotes the number of the successes. It's as the same as talking about the number of the successes over here. So it's number of successes over here. So by the another word, this type of the characterization determine that the X follow the binomial distribution. By the another words, I can write it over here that the X or the number of the successes follow the binomial distribution with two characters. The N, the number of the trials or the number of the statistical experiment is 8, and P or the probability of the success is 1 over 4. So we just write over here that the X follow the binomial distribution. I want to emphasize about it again. As much as you repeat it for yourself, it's gonna be helpful for you to understand and diagnose the type of the distribution in this type of the examples. So first of all, we have one trials, one type of the statistical experiment which is repeatedly done over here, and they are independent from each other. Means that the answering to the first question is independent from answering the question from the second one, and so on. So first, so let me just list all of these things that we have it over here to just follow it by, with each other. So first we have a trials over here, and what is the meaning of the trials over here? Means that we have some statistical experiment that repeatedly happen over here, and they are independent from each other. So second one is two cases that we have it, the binary case, I mean the failure and the success. So for each of this statistical experiment, the probability of success or getting the things that is our concern is constant, and it's 1 over 4, and the another one failure as well. So the another characterization that lead us to the binomial distribution is about the actually random variable. So our random variable is defined as a number of the successes. So it's important to know its number of successes. So because these type of the things are happen, we can diagnose the actually distribution as a binomial distribution. So first of all, we have a trials, means that we have some statistical experiment that are totally independent from each other, and the another one is the binary cases that we have. It means that for each of these statistical experiment we have the success and failure. We have two cases, not more than two cases. So we have binary cases or the failure and success, and this probability of failure and success are constant, means that it's not changed for the second question, for the third, and so on. And the another one is a random variable that determines the number of successes. So with knowing that type of the things, we can realize that the probability, the distribution follows the actually binomial probability, or X follows the binomial distribution with two characters. One of them is N, number of trials over there. The another one is P, which is the probability of the successes. So right now, if we want to know that what is the probability to answer 3 questions exactly correctly, so we should calculate it by the formula that we have it, and the formula said that this type of the probability is equal to 3 out of the cases that we have. It means that 8 times the probability of the success over here is 1 over 4 multiply to the power of number of the successes, which is 3, times 3 over 4, or the probability of failure to the power of number of the failures that we wanted, which is equal to 5. And you can calculate that value as well. It's gonna be 8 times 7 times 6, because you will cancel it with the 5 factorial at the denominator, over 3 factorial, which is 6. So we can cancel also these two values, 6 over here, and 1 over 4 to the power of 3, which give us the value of 2 to the power of 6 at the denominator, or 4 cube over here. 1 is 1, so the another expression that we have, it is 3 to the power of 5, 4 to the power of 3 as well. So at the end of the day, you can calculate that value as well. So the another thing that we want to know about it is about the expected value. We want to know that how many questions in an average will be answered correctly if we answer them by a random. So it's clear that when you just answer the question randomly, means that the probability of answering the first question is 1 over 4. And if we consider it for 4 cases, you should answer at least one of them correctly in an average. For 8 questions, we expected to have 2 questions correctly out of these cases. Let us see that if our conclusion or interfere over here is correct by the words, by the numbers or not. So the expected value of x, this random variable, or the number of the successes, or the number of the correct answer to that question, is equal to n times p. And n over here is 8, and p is equal to 1 over 4. So 8 times 1 over 4, as we expected, is equal to 2. So 8 over 4 is 2. So means that out of 8 questions, we expected to have the average of 2 correct answers in total when this type of the experiment repeatedly happen. When we discuss about the average of the happening, when we discuss about the value that determine the average or the mean of something that we are expecting, so we should use the expected value to calculate or evaluate that things. So I hope that with that question you review the concept of the binomial distribution. But let us discuss about the cases that instead of 2 cases for each terriers, we have more than 2 cases. So this is gonna be the multinomial distribution. Let us take a look at the multinomial distribution as well. So let us take a look at the multinomial distribution. In a definition, we have the following things. If a given terrier can result in a k outcomes, e1, e2 up to ek, they are the events that the probability of them respectively is equal to p1 up to pk, then the probability distribution of a random variable x1 up to xk representing the number of occurrences for e1 up to ek in n independent terriers is equal to the following expression, and this one is a type of the permutation or combination, the complex combination over here, that is equal to n factorial over each of them factorials. So let us take a look at this situation precisely over here. Indeed, in a multinomial experiment, it's a type of the statistical experiment that we have the following properties. So again, we have a terriers over here. N times repeated experiment. The experiment consists of n repeated terriers, is a type of the property for this type of the experiment. So let us consider that type of the questions that we had it over there. For example, if you have 4 multiple choice question over there, we have 4 multiple choice question over here. If we repeatedly just do that one, means that this is one times, this is the second time, and this is a third times. For example, we 3 times do that type of the experiment. Right now we have a statistical experiment that is repeated, and each material has a discrete number of possible outcomes. So the possible outcomes for each of them can be considered as a k outcomes. For example, at the previous example we discussed about the correct answer and wrong answer, so we can also have 4 choices for each question that the person answered to the choice A, B, C or D. This can be considered over here as a 4 cases for each question. On any given material, the probability that a particular outcome will occur is constant. Over here, the probability of getting A is 1 over 4, the probability of B is 1 over 4, C is 1 over 4, and D is 1 over 4 as well. So the differences between the multinomial distribution function and multinomial experiment with the binomial experiment is about the outcomes of each cases. The remains are the same. Means that first we have a material as well. We have number of the materials or number of the happening that they are independent from each other. Means that the occurrence of one cannot affect the another one. The another part is about the outcome for each cases. At the binomial cases we had only success and a failure. We had only 2 cases, but at the multinomial distribution, instead of 2 cases, we have more than 2 cases. The probability of each event, let us call the first event as a E1, the second one as a E2, the third one as a E3, and the last one as a E4. The probability of E1, E2, E3, and E4 for each cases, for each material over there, are constant, and the value is invariant for all of these things. The materials that we talk about it are independent. That is, the outcomes on one material does not affect the outcomes on other materials. These are the things that we had it for the binomial distribution as well. The only differences is about the outcomes, that each material has a discrete number of possible outcomes for the multinomial, but for the binomial we have only 2 outcomes. By the another word, the multinomial experiment is a type of the generalization for the binomial distribution. So for instance, we have some example over here as well that determine the binomial distribution, but let us take a look at one practical example to see that how can we use that type of the things. So let us take a look at this example to see that how the multinomial distribution is working. So over here, let us take a look at the question. Suppose that a card is drawn randomly from an ordinary deck of playing cards. As you remember that we discussed about the playing card and the deck of playing card that contains 52 cards, and that 52 cards split to 4 types: the spade, heart, diamond, and clubs. And based on that one, it said that then put back in the deck the card that you drawn it put back in a deck. This part of the things show that the probability of getting for example the diamond is not changed. If it's not returned back to the deck, then the probability is not constant for each drawn. I just want to mention it again over here. For instance, let us assume that this is the playing cards and you draw a card from that playing cards deck, and when you just draw the card and you return it back, the probability of a being diamond, for example, is not changed. But if you didn't replace it back, then the probability will be changed in a second materials or the third one, and also the materials will not be independent. That's an important thing in the question indeed. So this exercise is repeated 5 times, means that we have 5 times of repetition over here, 5 times that type of the statistical experiment or trial is done, and each of these trials are independent. So for each trial we have 4 cases indeed. So if I just consider that one, we have 4 cases. The cases that we have it to get a diamond will be 1/4, because we have 13 cards of a diamond inside of that one. For a heart as well, the probability of getting card as a heart is 1/4, and again we have 13 of them. For the spade as well, if you just take a look at the spade, for the spade card as well, the probability is 1/4, and at the end for the clubs as well, the shape is like this. I hope that I can sketch it very well. Is 1/4, and this probability for each time is as the same, is constant, is invariant, and this type of the statistical experiment is totally independent from each other. So out of these 5 actually happening, I want to get 1 spade, 1 heart, 1 diamond, and 2 clubs, the probability of these things. So if I just denote the events of getting a spade by E1 and the random variable of number of the spade as a x1, then the random variable for heart x2, and the random variable for getting diamond is x3, and the clubs is x4, then it means that I'm looking for the probability of getting x1. I can rewrite it or demonstrate this question by this form: x1 getting 1, so I want to get 1 spade, and x2 is equal to 1 because we want to get 1 heart, and x3 is equal to 1 as well. It's a diamond, is equal to 1, and also the x4, the last type of the cards that we wanted, is equal to 2, and the number of n, or number of the trials that we have, it is 5. This 5 is an addition of 1, 1, 1 and 2 together. So to calculate this probability, I said that you should use one combination to write 1, 1, 1 and 2 at the denominator, at the bottom of that combination, and 5 at the top, means that 1, 1, 1 and 2 choose out of 5, and the probability of the first item, the first event, which is 1/4 to the power of repetition of that event, which is 1. For the second one, we have 1/4 again. The probability of the second one is 1/4. To the power of the events is 1. And again, the third one is 1/4 to the power of 1. And the last one, the probability of getting clubs is 1/4 to the power of 2, or 1/4 square. So I just write the probability for each, and we can calculate it as follow. It's going to be 5 factorial over 1 factorial, 1 factorial, 1 factorial, and again 2 factorial, because 1 factorial is 1. It only needs to write it like this. And the last one is 1/4 to the power of 5. 1/4 to the power of 5. 1/4 to the power of 5 is as the same as 2 to the power of 10, which is 1024. So we can rewrite that one as 5 times 4 times 3 because of that expression that we have it over there, over 1024. So it will be 60 over 1024, 60 over 1024. However, you can even simplify it more than this, but it can give you some idea. If you round it up, the denominator to 1000, you can find the answer as well. So you can see the solution by the words over here, that how can we get the solution and the answer. The only differences between this case and the binomial is the cases that we have it. I mean, we have instead of failure and success, we have 4 cases. So we calculate the probability, and the result, as we expected, is going to be 0.05, means that this probability is equal to 0.05 at the end of the day. So we can take a look at the another example as well. over here we suppose that we have a bowl with 10 marbles. So it's instead of the bowl over here, we can consider the bag and determine it by a bag. It's easier to determine it by a bag over here. I prefer the bag instead of the bowls. And instead of the marbles, I just use the actually some balls over there. We have 2 red marbles. Instead of that 2, I just sketch 2 actually ball over here. It looks like a marbles. And 5 blue marbles. So we can sketch 1, 2, 3, 4, and 5 marbles over here, and the 3 green marbles as well. So let us put 3 green marbles as well inside of that bag, and we draw something over here. We draw randomly, select 4 marbles from the bowl. So it means that we draw 4 of them over here. And that word is important again to mention that the replacement is allowed. It means that with replacement we do it. So that small words, I mean with replacement, change the question totally. If the replacement is not allowed, means that without replacement we just take a group of marbles out or drawn from that bags, then the distribution will change to the hypergeometry. That small words can change the question totally. I want to mention it again. When the replacement is allowed, when we just replace it back and then again we take it out, means that the probability of getting green, for example, is not changed. It's totally independent right now. So it's an important word that we have it over here. With that simple actually phrase over here, we change the question totally. When you replace it back, let me just sketch it over here. For example, for the first one, the probability of getting the red marbles is 2 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 balls totally over here. So the probability of getting the red one is 0.2. If the replacement is not allowed, if we just take them out without replacement, then for the second one, the probability of getting red balls is changed, is not again 0.2 as the previous one. So it's important to understand this concept. When the replacement is happen, means that that type of the probability is consistently remains over there. It's invariant, it's not changed. So of course over here we have 4 statistical experiment, means that the number of n is equal to 4. We have 4 statistical experiment, and let me just put them separately over here to show the situation that we have it. So we have 4 balls or marbles over here. For the first one, if we determine 3 events over here, what is that 3 events? We have 3 colors, so we have 3 events. The events E1 determine getting the red event, red marbles. So it's determine the red one, the E1, the happening of that one. E2 is an event that determine the events that we get the blue marbles. And for the last one, I mean the E3 determine the probability of determine the events of getting the actually green one. So as you can see, these events are totally independent from each other in that case. And if the replacement is happen, then the P1 over here, the probability of getting red, as we calculated before, is equal to 0.2. The probability of getting blue, P2, let us denote it by P2, is equal to 5 cases out of 10, which is 0.5, and the remained P3 is equal to 0.3. And you can see it over here that this probability remains for all of cases that we have it. I mean the P1 is 0.2 here. For the next one it remains 0.2 for the next one as well, and 0.3 for the green cases, and 0.5 for the blue cases. So because the replacement is allowed and we did it with the replacement, this probability is a constant value. It remains true for the remains parts. Means that for the second one we have the same probability, for the third one we have the same probability, and for the last one as well. It's not change for them because the replacement is happen. If the replacement is not done, as I said it before, then the distribution will be changed totally. It's going to be hypergeometric distribution. That we will discuss about it later on. But over here, because the replacement is happened, so we can use the multinomial distribution to calculate it. And again, we can rewrite it like this. The probability that we get x1, the number of the red marbles over there, how many marbles we wanted, what is the probability of selecting 2 green and 2 blue marbles out of 4 selections. So the number of them will be 0. We don't want to have any red one, but x2 or the number of the blue marbles is equal to 2, and x3 or the number of the green balls that we wanted is equal to 2 as well. And the total experiment or terial that we have, it is 4 terial. You may put the probability of each also in that expression. So at the end of the day, the value will be 0 and 2 and 2. These are the value that we have it over there out of 4. And the probability, the corresponding probability is 0.2 to the power of 0, 0.2 to the power of 0. And then the probability of the second one getting blue is 0.5, so 0.5 square because we have 2 cases, and also 0.3 square. And I want to remind you that the 0 factorial is equal to 1. So we have the following things, means that we have 4 factorial over 2 factorial, 2 factorial, which is equal to 2 indeed, 2 times 2. And we have that expression that 0.5 square or 1 over 4 and 0.3 square, which is 9 over 100 as well. So this is the value of that expression. We can rewrite them as follow as well over here. So let us take a look on it. So by calculating the value, the probability will be 0.135. As I said it, the 0 factorial is equal to 1, and you can just replace 0 factorial by 1, and 0.2 to the power of 0 also is equal to 1. The result will be 0.135. This is the case for the multinomial distribution. So in the next example, we want to combine both of these distribution, means that the binomial distribution and also the multinomial distribution. Consider a class of the student that contains, for example, 30% of Asian students. So we have 30% of Asian student, 20% of the American student. Let us denote it over here, the American and Asian. So we have the Asian and American student, and the remaining students are from the other nationalities. So we have 50% out of the other nationalities. And moreover, we have the age classification in this class, means that 10% of the students are over 20 years old, and the remains are less than 20 years old. So 90% are less than 20 years old. So this is the information about one classroom, and we select, for instance, 4 students from that class, and these 4 students that we select them out of this class replace, and we select it again, means that the replacement is allowed. One student is selected, we replace it back, and the another one is selected and we replace it back. With that attitude, means that replacing them back in the class, the probability of choosing for example American student is not changed. change. It's remained constant over there. So the question asks that out of these 4 students, what is the probability that the probability of, let me just write it by the words, it cannot be expressed like this. It's better to write the actually question by the words over here. So the part A of the question said that out of these 4 selections, what is the probability that one is American, one is Asian, and the remains are from other nationalities. So this is the first part of the question. The second part of the question told you that what is the probability that none of them are over 20 years old. So these are 2 questions that we have it over here based on a first part of the question, because we have 3 categories. It's more than 2 categories. We should use the multinomial distribution, as you guessed it before. Over here we have 4 terrials. The number of the terrials that we have is 4. So we have 4 terrials, and for these 4 terrials, we have, for each of them, we have 3 cases: to be American, to be Asian, or to be from another nationality. So the first part of the question should be written like this: if we consider E1 as the events of being Asian, E2 be the events of being American, and E3 being from other nationalities, then the corresponding probability also denoted by P1, P2, P3 respectively, then the probability on the first part can be demonstrated as follow. I want that to have X1 means that from being Asian is 1, from the American or number of the random variable over there is equal to 1, and the remains are from other nationalities, means that X3 is equal to 2. So together we have 4 actually cases. So we have 4 as an n over here. Right now, to calculate this probability, we can use this formula. We have 1, 1, and 2 out of 4. Then the corresponding probability to the given numbers, I mean 0.3 is a probability of the first type to the power of 1, then 0.2 the probability of the second one to the power of 1 again, because we want to have only 1 American in that group of people, and the remains, which is 0.5 to the power of 2, and that value can be evaluated as follows. We have 4 factorial over 1 factorial, 1 factorial, and 2 factorial. Only 2 factorial should be considered over here. And also we have 0.3 or 3 over 10, 3 over 10, and also we have 2 over 10 or 1 over 5, and the last one is half to the power of 2, which is 1 over 4. And if you cancel the terms that you have it, you can calculate that one as well. Means that it's easily can be calculated. The 4 factorial is 4 times 3 times 2, and we have one more 3 at the numerator, so let me just write 3 as well. At the denominator we have 2 times 10 times 5 times 4, 10 times 5 times 4, and you can simply simplify that expression as well to calculate it. This 4 and 4 will be cancelled. We have 1 2 over here, and this 2 will be cancelled. The result is 9 over 50 or 18 over 100, which is equal to 0.18. So the probability is 0.18 for this case. For a part B, you can see that the classification of each trial is two cases. We can consider it as a success and a failure over here. Right now for a part B, we have two cases, as you can see over there. So one case is considering over 20 years old or less than 20 years old, and I want that none of them are over 20, means that all of them should be less than 90. So playing with that words can change the question totally. So at the part B, I'm looking for the probability of a success over here. We should actually define our random variable before that we want to rewrite it here. So X denotes the number of students who has a age under 20 years old years. So right now, by this definition, I'm looking for having all of them equal to 4, means that I want that 4 of them, all of that student, are under 40 years, 20 years. So for calculating this one, you should determine the binomial distribution, and now the type of the characterization that we have it here. X follow the binomial distribution with 4 trial, number of the trials over here is 4, and the probability of being under 20 years old is 0.9. However, you can use the complementary part and define the random variable as a person over 20 years. Then you are looking for X equal to 0, and that X is different, so the result will be the same at the end of the day. So over here, because we want 4 students, 4 of them will be actually out of 4, so the combination of 4 out of 4 is the beginning of that expression. Then the probability of that happening, or the success or getting under 20, is 0.9, so to the power of 4, and 0.1 the probability of failure to the power of number of failure, which is 0, and the number to the power of 0 is equal to 1. So at the end of the day, it will be 0.9 to the power of 4. However, from the multiplicative rule, you could solve that question as well, because the selection of them are independent, and I'm looking for the intersection of some event, the intersection of getting the first one under the 20 years old, and the second one under 20 years old, and third and the fourth one. And because they are independent, the probability of their intersection is as the same as multiplication of their probability, which lead us to the same value. So this independency is important because of this. And if it's not independent, if the probability is changed for each case, then you should solve the question with the different methods. Right now, if I want to recap this distribution that we talk about it over here, we talk about 3 types of the discrete distribution up to this point, and the first one was uniform, the second one was binomial, and the third one is multinomial. And in a binomial and multinomial, we have some trials. Then the trials are independent from each other, and each trial categorized to 2 or more than 2 cases, which make it distinguish between the binomial and multinomial cases. So I will finish the course over here, and we will discuss about the remaining parts, hypergeometric and geometric distribution, for the next lecture. Thank you for your attending.